Okay, thank you for the invitation. It's really nice to speak here, and also for coming up with this workshop topic. I find it like really interesting to discuss. And in this talk, the first third or so is also a bit more high level. I'm trying to introduce like this work, kind of addressing what this workshop is trying to push for, scaling robot learning. Okay, when I hear this topic, scaling robot learning, the first thing I wonder is where do we want to scale to? Where are we running to? Where are we going? I'm always thinking about this, about the whole field actually. And in this case, I mean, the word scaling sometimes I think could be misleading, because you might think that scaling means you just have to scale to higher dimensions or to more data. Or scaling could mean that we take existing approaches and just scale their performances, or we have existing this might be more debatable. We have existing benchmarks and we just scale the performance on these. But sometimes I'm wondering, like on a scientific level, really where we should scale to on robotics is more on more complex and interesting behavior. Not just scaling the things and science and methods that we have, but actually scaling what we can really solve and do. And I think that would be like the kind of right thing to think about scaling. So now that I talked about complex, interesting behavior, I have to kind of like make a statement what I might mean with that. And I'm going to put Igor's work first, actually, more. So this is amazing, actually. It's from 2012. It's pretty long. We're not going to see it the whole time, but it's really interesting, complex behaviors like these, and also like standing up, things like that. I put work from MIT here as an example for task motion planning work. There's much more, just taking this as an example. There's own work that I'm going to talk about more later. And then I think this is also a cool example of complex, interesting behavior, right, that we see. So I think interesting complex behavior, you get an idea. What I mean is that we have really very high general purpose competence to manipulate the environment as we would like to. Okay, so now to add a second point to this, this talk will be based quite a bit on model-based planning, like task motion planning. Actually, this is what TAM stands for. And let me, to make this point, just ask why should we even care about model-based planning? Because this is a workshop on learning. I think many of people here sit here and think I only care about reinforcement learning or so. Why should I care about model-based planning? Let me first give you arguments against it. And these are kind of like citations of comments that I get. First one, it'll never work. This was Chris Atkinson, actually, I don't know, a couple of years ago after I gave a presentation, he said, that'll never work. But he meant it in a nice way, I think. Okay, there's other like arguments against it. All these model-based assumptions, these are crazy to make and to code, to implement. And then once you have these model-based assumptions, then to do planning. And then perception will never work. I mean, model-based planning very often means that you have to understand the scene, create meshes, and then do planning. That'll never work. Precise tracking, even if you have a plan, it might not be a reactive plan. And how do you actually execute it? Partial observability. And then, I don't know, we are all quiet because POMDPs, we will never anyway work. Okay, so these might be arguments against model-based planning, argument for it, generalization. So I think, I mean, the generalization power of these model-based solvers, I find them personally amazing. And I think I find it very rewarding if I, do work like on model-based planners, and I sometimes they come up with plans or solutions that I think, whoa, that's surprising, that's cool. So I think the generalization that we see with model-based like solvers is really like amazing. And this now adds the point again about where should we scale to. I think it's that kind of generalization that we actually should aim to scale to. And I don't know how so. So the question is, how could robot learning bring us to that same kind of generalization that I find fascinating to see in some model-based planners. And in that sense, working on model-based planners is kind of like homework or so for me and maybe others to understand what is actually the challenges to do that in the real world, and then think about how to realize the same things then and the same complex behaviors in a real world. I'm not doing all of this. Okay, so this was kind of like my first introductory comments, and now a bit more concrete. The concrete work that I'm going to talk about in this talk, actually two topics. The first one will be about using learning methods, machine learning, to enable the same kind of solvers that we've been working on a couple of years on, purely on images. So this is, related to many like work trying to do only image-based reasoning or visual foresight and things like that. And there's a couple of papers I'm going to talk about. And then the second part will be about getting these kind of solvers and solutions actually into reactive control. So we made some advance to design some MPC style execution like system for these. Okay, in order to talk about these, I need to at least briefly now also mention the kind of solvers that we've been working on. I haven't really explained them yet. So these are examples. This is like in RSS 2018. This is like one of the earlier works where the only target was actually here defined by touch the red ball, or blue is supposed to touch green. This is the only target, and the rest is just reasoning. And this is with a double hook and things like that. So we kind of extended this also to architectural applications, if this works. Yeah, it takes a while till it starts. We also like extended this to more physical interactions, where it's not only like reasoning about more kinematic style things, but also like physical forces and where to apply force, to put the tip at the right place to exert a force from the same thing. This is also about pushing. Pushing is surprisingly hard, but okay. And this is a funny thing about a walking robot trying to get to this yellow banana there. Okay, so these are kind of like applications of the solvers, and it's the same solver behind these kind of things. And what does that solver look like? So we formulate this as logic geometric programming, so programming in terms of optimization, and we write down this optimization problem. And all the videos that you've seen, well, kind of are the illustrations of the solution of that mathematical program. Not simulation runs or anything, but they are an illustration of the solution of that mathematical program. So this mathematical program is describing manipulation sequences. And this is the major point I need to get across in order for you also to understand the rest of the talk, is that, I mean, there's just some boilerplate notation here. But the point is that there is many constraints involved in the mathematical program, and these constraints define what is correct physics or what is correct manipulation. And they will play a central role in a second. And I had to like code them, right? And this is the ugly part. So I had to write down equations, what correct impulse exchange means, what correct flying means, what correct pushing means, and things like that, in order to put it in that mathematical program. Right. And then there is a second aspect about this mathematical program, namely that it actually tries to organize the search over solutions by searching over schedules of physical modes. Every physical mode is something like a contact mode. It's like a mode of interaction with objects or between objects. And within these modes, we assume that all these functions are smooth. And that structure is fundamental to how to solve that. And so really briefly, in a nutshell, just what does that mean to solve it? So solving such a mathematical program requires you to iterate searching over the sequence of modes, like interaction modes or physical modes. And then once you fix the sequence of modes, that actually translates to normal nonlinear mathematical program, and you try to solve that. And it kind of cycles like that. So the sequence of modes, we actually use a logic language, PDDL language, to define that. And this defines the sequence of modes. And if you have the sequence of modes, that defines what kind of physical constraints you need to fulfill, that defines a large mathematical program, and then you kind of cycle through that. Just really quickly. Okay, now to the first topic, learning. Given that setup, how we did some exercise in trying to generate complex behavior based on models, the question is, how could we enable doing this based on images? Because what I described so far requires full scene descriptions, mesh models, standard planning, robotics planning stuff. How could we do the same thing just based on images? Well, the key thing is the feature functions, the constraint functions that I mentioned before. So those guys here. In the model-based approach, these functions are all defined based on the meshes and the exact scene description and everything. But what if we can replace these functions actually to be functions based on images? So we keep everything else, the mathematical program, the solver and everything, but replace these actually constraint functions in that mathematical program. So this means what we need is differentiable functions, need to be differentiable, otherwise we could not use efficient optimization, that describe what is correct physics, what is correct grasping, what is correct hanging in terms of like a discriminative function. or like equality constraint function. And I made that statement already, like, do we actually need meshes and shapes and to define these functions by hand, or could we just learn on images? And that's exactly what what I'm going to talk about. You could define these functions based on image and train such a mapping. Okay, how? I think many people would have now ideas how to do that. It's kind of a common thing done today. I wanted to mention that we've kind of realized this in two different contexts. The first one is work which implements task constraints such as describing correct hanging and grasping, which can then be incorporated into the planning system. And the second one is actually describing correct physics. So, describing learning dynamics models, basically based on images, so that they can also be incorporated in planning. And this is joint work also with people from MIT. I missed some pictures here, Yak Su, I don't know if they're here, but also people from my lab, especially Danny, and Danny will talk more about this also Friday, and a postdoc of mine, Jiangsu. Okay, and I'm going to focus here first on that second part. So how can we define constraint functions based on images? Okay, so we basically in our lab moved or started to like more and more the idea that we represent objects not in terms of meshes, but in terms of fields. This is at least my words. You could also like say implicit functions or different words for that. So what does that mean? The pipeline is like that. We assume that we have multiple cameras looking into the scene, 2 or 4, something like that. And what we want to learn is a mapping from all of these 2 or 4 camera images onto a differentiable function over the configuration, like configuration variable x. That's this phi. This is what we need for our mathematical program. We do that by first actually training and embedding like a representation so that every object is represented by a d-dimensional field over the 3D space. And you could call this a pixel-aligned implicit functional object representation, just call it a field. And how is that done? Well, you take every camera image, and also the cameras need to be calibrated. That's kind of the K. And for each of them separately, you use a unit to map this onto representation. And then together with the camera pose, you also then have another like layer, which is this multi-layer perceptron. And actually, I'm describing this little figure here on the left, which is first a unit, and then there is a multi-layer perceptron. And you kind of average these images from different perspectives in order to get this field, like a d-dimensional field over the 3D space. So it takes the space as an argument. And now that means we have represented the object as a field. And now, in order to finally get the feature, we can query that field at some points, for instance, like points that represent the grasper or the gripper or something like that, to get like a finer dimensional like feature from that field and use yet another multi-layer perceptron to actually get the feature. And that feature is used in a mathematical program to actually do planning. Training, I just explained you kind of like the pipeline for that function, but the interesting thing is actually how to train these representations. And really what makes a lot of sense is that you train these representations for multiple decoding tasks. So these field representations, they need to be sufficient, or we trained them to be sufficient also to predict the signed distance function to objects for which we have a model. That's a very, very strong like signal, because essentially we require the field to represent any information that relates to shape. In another work that Danny is going to talk about like on Friday, actually we also trained him to be like, that they can decode the image. So this is nerves. So we have a nerve decoder. And that's, separate, or in addition to also train him to actually predict correct like grasping or hanging. And how can we actually train them to predict correct grasping or hanging? Actually from empirical data. So we actually take empirical data in a simulation of many poses of grasps, or like poses of mugs trying to hang them or so, and collect the data. And then by this kind of trial and error kind of data, we train that representation to also be predictive for that. Okay, so in a sense, it is also like learning like from the data and from trial and error data, but it's learning in a much, much structured approach where we learn these constraint functions, which can then be used for execution and planning. And here is like a first little example where you use these trained constraints within the same like optimization framework that I described before, to generate sequences of first grasping. So also the does this start? Yeah. Also the grasping here is learned. So based on a like neural net feature, and also the hanging. So it's trying to hang it here onto that thing. I'm going to start this one at the same time. So there's much more evaluations for like mux that it has not been trained on, trying to do that. And depending on how close the mug is on the training data, it has higher success rate, lower success rate. Okay, and that generalizes also to different mug shapes, which were completely not in a data set. And also like here we have actually another thing for handovers. So the same features that were trained could now also organize a handover or translate to like another like hanging structure, which has more pieces and things like that. Just, yeah, because they generalized and just in general learned what is the correct hanging. Okay. I mentioned it already. So Danny Dries also like extended this in actually a bit more elaborate. So this was kind of a simple like demo that you can use really trained and learned features in order to embed them in this mathematical program, trying to yield the same generalization power. And here is a piece of work that tries to do the same thing, not for task features, but actually for dynamics. And that is strong enough, for instance, also to predict dynamics of deformable objects or yeah, dynamics of pushing, which is actually surprising hard. And in a sense, this is like very similar to visual foresight. I guess everybody knows that kind of work, but it's very like long-term stable to do that. So we can really predict like sometimes hundreds of steps, and it's still visually stable and allows therefore for planning. Okay, second topic, need to watch time. So far, this was mostly about planning, also planning based now on learned features, but the same kind of framework, which represents actually the full behavior in terms of an optimization problem, but it's not really reactive yet. And so the question is how to make this or turn this into a reactive control framework. I'm gonna go a bit quick over that and maybe spend a bit more time than on the video if I have. Should be fine. So, the solver, this optimization problem, logic geometric program that I showed, is a task motion planning solver, and it's surprisingly hard to actually get this to reactive execution. I want to mention this work. I'm really fond of that one. It's really strong. This is actually reactive execution. Should read it. It's cool. Anyway, so for us, it's not so obvious and trivial, although it's an optimization problem, how to get this to reactive execution. And that's the reason kind of is that the control infrastructures that are typically used on robots weren't really mathematically consistent, I'd say, to this logic geometric programming, or at least I found it not consistent enough. If you do some typical operation space controller, I don't know what your control infrastructure is, it's not perfectly consistent to that logic geometric programming. And that work is actually trying to think about what is a consistent control infrastructure, for executing these kind of these plans. So like we introduced a different type of notation, which doesn't, it's basically the same as what I described before, that the problem is an optimization problem where different constraints hold in different phases. We just use a different notation, and basically that notation says that the problem has constraints which are about the waypoints. So you have to go through that waypoint, that one. And between waypoints, there's other constraints that hold. And all of these constraints are functions that are learned or not learned, coded, right? But they're differentiable. And basically the problem is to kind of fly through these constraints in a time optimal way. How can we actually realize this in a model predictive control framework? The key thing is to decompose this, because if you try to like directly do some typical finite horizon MPC approach, that doesn't really work. And so what we're going to solve for in every MPC cycle, is that we are like optimizing first just the waypoints, like what are possible solutions for these waypoints, for all of them. And that's a very like long horizon solution that you generate within the MPC problem, so that the MPC cycle actually always maintains long-term goals, so sub-goals. At the same time, and the timing optimization is actually really important. If you want to go through constraints, understanding when you should go through these constraints and not fixing the absolute time is really essential. And it's a major thing of that work also to do this timing optimization. And then finally, there's also the more typical standard part, which only optimizes a smooth, fine resolution path for the next half second or something like that, which is the more conventional MPC kind of thing. Okay. Okay, I just dumped the pseudocode here. We won't be able to understand this here. The easier part to explain that is like the lower part. In every, like with 10 Hertz or something, like in every line, like cycle, we solve for the waypoints, for the timing and short horizon. And the cool thing is that therefore this control is really reactive to things that influence the future, because it's maintaining the future estimates of future waypoints that can be very long, to go. And also the timing of these waypoints. There are some other parts of this whole thing, which is about the phase backtracking, meaning that if you lose some constraints, you're actually going back in that sequence. But rather than to explain this, I want to actually show this in video. Now open this separately so that I can jump to the second part. So this is a normal, like a pushing maneuver, what's going to come here. And actually I should stop this already. The goal here, the only constraint of that mathematical program is at the end of the manipulation, the red will touch green. And there is one phase, which is the pushing phase, and another phase, which is the approach phase. So actually the structure of this whole manipulation is approach it, push it, and then red will touch green. That's the only thing. But if you execute it, reactive execution is really involved. It just cycles and redoes the thing. The reason is that while it's pushing, it's always actually losing the running constraint of a push. And when it's losing the running constraint of the push, this cycle that I just showed automatically cycles back into the previous constraint. It's like if you wanted to go through a constraint and missed it, you cycle back and you try to do the same thing again. Okay, let me just continue showing this longer. And I'm never stopping this thing. So this is just running endlessly kind of. And it's obviously reacting to where I'm moving the red thing. And this one, this one actually is an interesting one. You see that I'm kind of changing the future constraints. And it's really a future waypoint, right? It's actually pretty far away from the point of MPC. But it's even understanding that the current approach is infeasible with respect to that future constraint. And so I have to like backtrack again and do the approach in a different manner. And it's also reactive to that. So this shows that like this short horizon thing is also like reactive to interventions like that. Okay. And the former part is just about objects, I don't know, being stacked. And it's pretty similar. So this is just a normal, like a stacking sequence. And I can also like be nasty and try to do all kinds of things. And yeah. Okay, so I'm kind of like happy that because this really also on paper, like mathematically bridges between the LGP formulation and the control infrastructure, which I think is really nice. And it relates to an earlier discussion that I had in an RSS paper. I'm not going to mention this for the sake of time. To conclude, I guess time is over. So I had this thing, that kind of generalization is what we want or should maybe scale to. And well, so I think the kind of work, this model-based kind of planning, to me at least, demonstrates really nice complex behaviors. And I think this is, what we should try to scale to. And in my view, I think like just the training, like if we have lots of data, if we have the objectives defined, so we kind of know nowadays in the field how we can train the hell out of neural networks. We kind of understood this, and scaling just these kind of methodologies might not be the thing. To me, it's more the question of, well, how and where actually should you leverage these kind of hammers, these methodologies, right? And in this percentage work, in a sense, it did a whole of homework to think about what would it mean to do complex behavior in terms of planning, and then applies machine learning to some components of these. So we have a very pre-structured architecture saying we use LGP, but then all the things that define the LGP potentially could be planned, right? So it's applying machine learning on the components. And you could argue this is not cool because end-to-end is better or so, but I'm kind of wondering or asking the question, very often nowadays, we are very innovative and creative in predefining structures, like neural structures very often, like how we design these systems. I feel that many advances actually are exactly in how we predefine these structures of the systems. And in a sense, I feel that this is really justified also here, that we as robotics engineers, if we have a really good idea of how the control infrastructure or reasoning infrastructure should be, that we should try to think about how we can take that structure, but still enable, powerful deep learning or something like that. And this is what this work tries. Thanks for your attention. And this is my team. Yeah. Thank you.